Lesson 9.4 is about hyperbolas. Our essential question is, how does the equation of a hyperbola relate to the features of its graph? So the hyperbola is the last of our conic sections. Just like with the ellipse, we can have a horizontal hyperbola or a vertical hyperbola, and that changes the equation slightly. So a horizontal hyperbola, you'll notice, has the x squared first, and a vertical hyperbola has the y squared first. And you'll notice the difference in equation between this and the ellipse is that there's a minus instead of a plus. There's also asymptotes, and those are a ratio of our a and b values. So that also ties into kind of the shape or how wide or narrow the hyperbola looks. We also have a different relationship, so it's still a, b, and c, but we have a different relationship to find the a, b, and c values. Our c is equal to the square root of a squared plus b squared, so a little bit different than ellipses. So our first example says, how can we derive the equation for the graph of a hyperbola? So what we're looking at is the graph of x squared over 9 minus y squared over 16 equals 1. So you can see there's an illustration to show that the distance between the focus, like each focus and the hyperbola, is constant. So this distance is constant. The difference of the distances is going to remain constant the whole time. So the distance between one focus to the hyperbola and then the other focus to the hyperbola. So you can see this relationship drawn out right here. So d2 minus d1 is going to be 8, because we can see that when it's flat horizontally. 8 minus 2 is going to equal 6. So that means no matter where you moved that dot along the hyperbola, that 6 value is going to stay constant. So how this relates, so our 3 right here is our a value. So our a squared is 3, which turns into the 9. And then the b is visible more with the asymptotes. So on this one, since this is a left and right hyperbola, our asymptotes are going to be y equals plus or minus b over a. And so our b value in this case is 4, and our a value is 3. So that means that our asymptotes are at plus or minus 4 over 3. So if we were to graph that and go up 4 over 3 and down 4. So it's kind of, here is one asymptote and the other asymptote. So that's kind of helping shape what our hyperbola looks like. Okay, so we're going to write the equation of some hyperbolas. The first thing we're given is vertices at 0, -3 and 0, +3. So right there, what that tells me, having troubles with the graph here, does not want me to make a point. Okay, so we know that that's going to open up and down. And then it gives us the equation of the asymptotes. So that actually is helpful too, because that's helping us find our a and our b value. So we know that this one is going to be y squared minus x squared equals 1. And then we know that the asymptotes of a hyperbola that opens up and down is going to be plus or minus a over b x. So that tells us our a value is 1. So 1 squared is just 1. And our b value is 2. And 2 squared is 4. So that would be our equation with that information given. Part B says what's the equation of a hyperbola with foci at -3, 0. Does not like me to draw dots. And +3, 0. Okay, and vertices at 2, 0, and negative 2, 0. So that tells me that this is going to open left and right, and there's my vertices. So I know that A is 2, and I know that C is 3. So I can use that to find B and write the equation. So we know that C is equal to the square root of A squared, which would be 4, plus, oh, I should put C here instead of, so C squared, so 9 is equal to, let's start over here. Okay, I like to think, let's do it as C squared equals A squared plus B squared. So 9 is equal to 4 plus B squared. So that means that B has to be the square root of 5. Because if we subtract 4 on both sides, we get B squared equals 5. So B is the square root of 5. So this one is centered at the origin, and it opens to the left and right. So we know it's going to be x squared minus y squared equals 1. Our A value is 2, so that tells us that we're going to square that and get 4. And our B value is the square root of 5, which means we square that and we get positive 5. So there's our equation. Our last example is kind of a wrap-up of the conic sections, and it's how to classify the conic sections. All of these you could put into standard form. You could complete the square and put it into standard form, but you don't necessarily need to do all of that work in order to identify which conic section it is. So for example, on A, I notice that I only have one variable squared. I have x squared, but y is not squared. So automatically, I don't need to do any more work. I know that that has to be a parabola. So parabola is the only one that has only one of the x and the y squared. What I notice on B is I notice that the x squared and the y squared both have the same coefficient with them. So they're both a 1, which means even if I complete the square and divide by a number, that means that I'm going to have the same either denominator or same coefficient with both of those. So that tells me that this has to be a circle. And then the next one, I noticed that I have different coefficients with the x squared and the y squared. And I can see that there is a plus between the x squared and the y squared. So that tells me that this would have to be an ellipse. And then our final one, I have different coefficients with the x squared and the y squared, and I see a minus. So I know that that's going to turn into x squared minus 9, or 8x squared minus 9y squared, which tells me that this would have to be a hyperbola. So that is how you can tell without having to do all the math of completing the square.